All right. Okay, so in 25, it was the vector u was the vector negative 8, 3. All right, and we wanted to write u as the sum of two orthogonal vectors. Now, the one we just got was negative 6.3, negative 2.1, was that right?
Yes.
Okay, so negative 6.3, comma, negative 2.1. All right, and now we're supposed to add to that this other vector. All right, and so what we did in class last time was we just put a's and b's there. So we'd get negative 8 equals negative 6.3 plus a as one equation. And then we would get 3 equals negative 2.1 plus b as the other equation. So here this would be 5.1 and this would be negative 1.7. And so we would just put those two numbers in here. So this would become negative 1.7 and 5.1. Okay, now you can check this this way. Add that. I need to point at that because we're recording. I think we're recording anyway. Add that to this, and it should give us this one. Add this to that, and it should give us that one. Okay? All right, so that's 25. All right, let's look at 29 quickly. 29 takes a lot of time, and so I may not wind up doing all of 29, but I'm going to show you enough that you can see what you would have to do in 29 to complete it. All right, it says, find the interior angles of the triangle with the given vertices. All right, let me get some graph paper here so we can make it look right. All right, so the ordered pairs that we had here were negative 4, 5, all right, 1, 10, and 5, negative 1. Okay, now I'm going to connect this to get the triangles, and then I'm going to do what we need to do with this thing. All right. What they ask us for here, it says find the interior angles of the triangle with the given vertices. So now, if I want to find those interior angles, we actually have two ways we could do the problem. So I'm going to tell you both of them, and then we're going to do it the vector way because that's what they want us to do here. All right. One thing we could do is we could use the distance formula to get this length, and this length, and then we could use the law of cosines to get an angle. So, like, if we were going to get this angle, once we knew this side right here, so I'm going to just put a little a here, a little b here, and a little c here. We could go a squared equals b squared plus c squared minus 2bc cosine of the angle A, where this would be the A that we were looking for there. We could do it that way. Now, that takes a certain amount of time because you got to use the distance formula 3 times, and then you got to use law of cosines once. Okay? So now, what we want to do is we want to beat the time on it by doing it as a vector problem. All right? Now, the other day we had this formula that said the cosine of theta, where theta was the angle between two vectors, was equal to the dot product of u and v, all right, divided by the length of u times, it's the length of u times the length of v. Okay? Now, when I was teaching this, I told you that this formula actually comes from the law of cosines. All right, but we didn't derive it. It's on page 516 in the book. But if I want to find angle A, what I need to do is I need to have a vector AB. And then I need to have a vector AC. And then I can use the law of this rule to get the angle between the two vectors. All right, so if I want to get AB right here, remember that this is a directed line segment. And so when I get this, what I'm supposed to do is I'm supposed to put the x coordinate of B minus the x coordinate of A. It always goes tip minus the tail. All right, so here we would go 1 minus 5 and get -4. All right, and then to get the y coordinate, it's the 1 of B, so it's the 10 minus -1, and we'd get 11. All right, and now we need to do AC. So when we do AC, since the C is the one that's at the tip, we've got to go -4 minus 5, and then we've got to go 5 minus a -1, like that. So what we have here then are two vectors. And then if we want to get the angle between the two vectors, now we need the dot product of these. All right, so just so I don't have as many symbols floating around here, let's think of this one as being U, right there. And let's think of this one as being V, and then just plug into that formula. So if I do the dot product here of these two, in other words, I could write that just this. The dot product of this with that. That's probably the better way to write it, but I was trying to get the symbols to be shorter. All right, that's just going to be -4 times -9, which is 36, and it's going to be 11 times 6, which is going to be 66. So that's going to be, what, 102? All right, so that part's 102. Now I need to get the magnitude of AB, and then I'll need to get the magnitude of AC. All right, so on getting the magnitude of AB, remember it's the square root of A squared plus B squared. So if we come back up here, it's going to be this number squared plus this number squared. So that's going to be the square root of 137. And then on AC, it's going to be the square root of this number squared right here, and then this one. And so that's going to be the square root of 117. And now we just have to put all of that in the calculator. Okay, so let me just write right here. I'm going to write in a different color just so it'll stand out. All right, so we're getting cosine of theta equals, all right, now our dot product was 102. All right, and then we had a square root of 137 and a square root of 117. And so now we can use the calculator and we can get that angle. Now, I'm going to finish this one, but once you do that one, then what you're going to have to do is you're going to have to come up here and get the ray CA and then the ray CB. Now, CA is going to turn out to be the opposite to this one. So CA is going to wind up being 9, -6. I'm just going to say that because when you start to do this, if you go one way and you get these two numbers, if you go the other direction, it changes the sign on those two. Okay? And so when you're getting angle C, you'd have to have those two. Now, let's just do the rest of this on the calculator. All right, so we want the cosine inverse, so second cosine and then we want the 102 divided by, and we're just going to put square root, and we're going to put both those numbers in the square root. So 137 times 117 there, and press enter. And so the angle that's right here is going to be 36.3 degrees. Okay. Now, let me put this down for a second, and then I'll answer questions that you have. Do you understand what I did to get that? All right. And then you just got to do that twice more to get the angle that's here and the angle that's there. Michael?
Do law signs at that point.
Could we do that? All right. The only thing that's keeping us from it right now is we still don't know the lengths of those sides. Okay.
Did you find the lengths of the sides of them? Just do law signs.
Well, let me ask you this. Did we not find the length of side AB right here? Okay, so in other words, we could write that this is the square root of 137, and this is the square root of 117. Okay, and yes, we can do law signs then. Yes, I never thought about doing it that way. I just think of it as a vector problem after that. But yes, you could do the law signs to get the second angle, and then you could subtract from 180 to get the third. Okay, now just a quick thing here, because it came up on the trig test, but we haven't gone over the test. I just allowed you to look at them for just a second or two. All right, depending on how you do something in a trig problem like this, if you do not use the fact that last angle is 180 minus the sum of the first two that you have, but you use the law of sines to get it, then you may get the angles to not add up to exactly 180 because of rounding in the problems. Okay, now, since the way I'm doing this one, we're getting this to the nearest tenth of a degree, all right, then you should not be off more than 3/10 of a degree because you couldn't have rounded more than 3 times in the problem, okay? But when you're rounding it to the nearest degree, sometimes some of you got angles that added up to 181 degrees, which is okay if you do the problem that way. You just understand, wait, there's a rounding thing that's going on here, and because we're rounding to degrees, then we get that. And it depended on how you did the problem as to whether you even had to think about that or not, because a lot of you just did the problem like there was one where you did a law of cosines first, a law of sines second, and you just added the two angles and subtracted from 180 to get the third one. But it depended on which angle you found first. You can actually get two different sets of answers in one of the problems. And so we'll go over that someday. Okay. Now, do any of you have a question about this? Because I think this was the hardest type of problem right here. And then if we go back to the 25, where you have to find the projection, and then you had to get the sum of the two vectors that were orthogonal that would add up to u, and that's what 25 was. So we've done something like each of the hard ones. Okay. Now, the topic today changes a bunch. We're not going to talk about vectors for the rest of the chapter, but do you remember how when we were doing the stuff about vectors, we had a cosine of theta and a sine of theta that crept into everything? All right. In this stuff that we're going to do, we're going to get something about cosine and sine creeping into stuff too, but it's going to be basically a different topic, but it's all related, which is why it's in this chapter. All right, so. It was fun. Okay, all right, like you. Wait. Hold on.
Yeah, my first triangle was 3-1.
All right, that's my fault. I read the last point as the 1 in 30, instead of the 1 is 1. I wish you always said that earlier. All right, now, what I will tell you is the technique I used is right, but because I'm using a different point, then I lost that. Don't let me do that again. All right, have mercy and just tell me, you're an old man, you're acting stupid. Let's get on with it. All right, make the correction. See? I don't mind getting older. I do mind getting stupid. So. All right, what we're going to talk about in section 6.3 here are parametric equations and motion. All right, now, first of all, you will need to have good batteries in your calculator. It's not like you need to change them out, but if yours are weak, we're going to be highly calculator driven for a little bit. Okay, now, in this chapter, well, let's see, instead of saying in the chapter, let me take the calculator out one more time. All right, I want you to look at the mode key here for a minute. Let's see. All right, I want you to look down on the line right here where it says function. All right, now we understand the concept of function. All right, if we have a function, then it's in the form like y equals f of x. And f of x could be any number of things. And we know that the calculator can graph it, and we can do things like get maximum points, minimum points, and where it crosses the x-axis, etc. Okay? All right, so that's what function right here represents. All right, now, if we will toggle over one here, all right, and get to parametric, then we did something just like one day, just a little bit thing about what parametric looks like. Well, when you do parametric, and you're going to see this in a minute, when you go to the y equals, it's going to give you an x1 equals, and it's going to give you a y1 equals, and then we're going to get functions over here, but these are going to have a third variable, t, as the parameter. Okay, and I'll explain all of this as we go through the lesson today, but when you talk about parametric equations in motion, parametric equations, there are going to be two of them, one for x and one for y, and then there's going to be another variable t that occurs in it, okay? Now, later in the chapter, we're going to deal with what are called polar coordinates, all right? And so if we go over one more right here, you'll see that it's polar, and when we do polar equations are in the form r is a function of theta, and the r and the theta are not just substitutes for x's and y's. They have different meanings to them, okay? So by the end of this chapter, we're going to know 3 different ways that you can represent an equation and it draw into a graph, okay? Now, the reason that these are going to be different from each other, the big deal reason is this. Remember, if it's in the function form here, you cannot make your graphing calculator, if you just write in one equation, graph something that's not a function. In other words, everything it graphs will pass vertical line test. Okay? Now, when we start graphing these things in a few minutes, we can get a bunch of interesting shapes. And it doesn't have to pass the vertical line test. For example, we might get something that looks like that, okay? And everything about what causes things to change, what causes it to look like it looks, changes from what it is in function mode, okay? Now, later, when we get to the ones that are polar, we're going to get a bunch of really cool things, that look like that and that kind of thing, all right? Now, all of these things that we're getting that are going to look different from each other have to be studied and it's sort of separate entities. All right, you've basically spent about 2.5 years studying this. All right, you might at one day in one class have talked about this for 20 minutes. Now, we're going to talk about this for today, the next time, and part of the next one. All right, we get the easier stuff today, we get the more complicated stuff next time about the graphing of it, and then after that, we go into where we're doing this. So what you need to understand is basically in the rest of this chapter, they're going to introduce us to some things that are just different than what we've known, but it's going to be vaguely related to the stuff about vectors, so it's in the same chapter. All right, now that's a long-winded introduction to something, so let's get into it and do something with it. All right, now the part today that we're gonna deal with are just first of all just what is a parametric equation, or what's a set of parametric equations, and then we're going to talk about what parametric curves look like. We're going to learn the things that cause them to do what they do. All right, and then we're going to talk about something called eliminating the parameter, and that's about the part here about lines and line segments is where we begin next time, and simulating motion with a graphing calculator. That's going to be next time. All right, so let's just plunge into this. All right, this is the definition: the graph of the ordered pairs x, y, where x is a function of t and y is a different function of t, in other words, it's got a g there, are functions defined on an interval I of t values is called a parametric curve. All right, so anytime they give you the two equations where it says x equals and y equals, and the independent variable over on the right side is a t, that's going to be a parametric curve. All right, the equations are called the parametric equations of the curve. The variable t is called a parameter, and the I right there is called the parametric interval. All right, now this part here where it says an interval I of t values, I want you to think about this as corresponding to the word domain in functions. Remember, the domain was the replacement set of x. All right, and so this interval they're talking about will be a t interval, and it will be the replacement set of t, so it acts like domain does. All right, now here are some facts about parametric curves. The independent variable is t, and it usually represents time. Okay, the graph is graphed in an xy plane just like functions are. So let me just make a drawing down here as we go through this. All right, here's an x-axis, here's a y-axis. All right, now, a lot of times when you get a parametric curve, it's going to represent something that could happen in a science class a lot of times. Now, it doesn't have to be that way, but that's where the practical use is. Let's suppose for a second that we were at Cape Kennedy, all right, and we were going to launch a rocket, but instead of it going around and circling the Earth, well, let me tell it to you this way. In 1959, the Russians had already sent up a satellite that could circle the Earth, and they had a cosmonaut in it, and American schools all of a sudden, well, America reacted with fear, because whoever could conquer space, they could put intercontinental ballistic missiles out in space and could shoot them at the other one and could conquer the world. And I cannot convey to you the fear that existed about that happening. Okay? All right? I was in the 9th grade when the Russians shot their guy up. Now, we were behind in our space program. All right? Which meant that we had not done a good job with math and science. That's the way it was interpreted. And so all of a sudden, math class became harder. It was like, we got to catch up with the Russians, because if we don't, they will kill us. All right, that was sort of the fear. Well, anyway, I was sitting in 9th grade English class when America shot its first manned rocket up into space. Now, all it was Cape Kennedy was Cape Canaveral back then, and Alan Shepard went for a little 15-minute ride and wound up landing down in the Caribbean. Okay? Now, but I want you to picture this for a minute. Let's suppose that this is where he starts. All right? Now, if you shoot a rocket up in the air and it doesn't go into orbit, then it's going to go up and it's going to come back down. It's just going to be basically a parabola. Like, when Mr. Hasselberg shoots off rockets, they just go up, they come back to the ground, but you predict all this different stuff about them. Okay? Now, the reason we might want to describe the flight of that rocket in terms of parametric equations is this. Now, again, I want you to picture that right here is Cape Kennedy, and then the plane is the spacecraft, the little 8-foot around thing, whatever it was, all right, is just going to go up in the air and come back down like this. So, do you see that it is going to have a height that it is at a certain time? Okay, in other words, it's going to be a certain height above the ground. But it's also going to be downrange from Cape Canaveral. All right, but it's going to be at this place at a certain time. Okay, so basically what we want to know when we use parametric, where t is going to represent time, we want to know where it's at as far as like height and distance away from this point, horizontal distance, as a function of time. So at time 0, he's still on the launching pad right there. But then 5 minutes later, then he's up in the air like right here, all right? And so he's going to be a certain number of miles southeast of Cape Kennedy, but he's going to have a certain height. And so we're going to get this ordered pair that represents his distance down. I don't know how do you refer to that distance? It's what is it?
Away from the base.
It's his distance away from the base, but you call it when it's if it's military and you're chasing something that's downrange. There's some word like that you use for it. I can't remember it right now. But anyway, we're going to get that. But they are going to be functions of time. In other words, if after 5 minutes is here, after 10 minutes is here, after 12 minutes is here, etc., we want to know where he's at based on time. We need to be able to predict his flight. Okay, so that's basically the idea of why we need something like parametric functions, is that sometimes we need that third factor of time in the equation. All right, so now in what I've told you right here, where it says the graph is graphed in the XY plane, we still have an x-axis, we still have a y-axis, we still have ordered pairs x's and y's, but the way we get the x's and y's are based on the variable t. All right, now to graph them on your calculator, you have to be in parametric mode. All right, and then we'll go back and do one of those in a minute, so you do that. Number 4, the parametric interval for t is the domain that you're using to graph the function, and you input the parametric interval into window. All right, now, and window is going to look different in parametric than it did. All right, in 5, parametric curves are rarity functions. Most of the time they don't pass the vertical line test. And with parametric, when you're in function mode on your calculator always graphs from left to right, no matter what. So since it graphs from left to right, we don't need to draw arrows to indicate motion is left to right. We just assume that's what it is. But in a parametric curve, the parametric curve may do something like this. And if it does, we put arrows on it to indicate the direction of motion. Because in parametric, you see, when we look at it later, we won't know it started here and wound up here. We might think it started here and went in that direction. And so we put arrows on it to indicate the direction of motion.
So will it show you the direction of motion when you graph it?
Well, you will see the graphing, and then you have to then put the arrows to indicate which way it went. All right, now, as you get into this, most of you actually like this because it's sort of cool stuff. And it's just that if we have to do something where it's really hard to get a function, that can be difficult. All right, but that's not in this class period. That's in the next one. Most of what we're going to do today, you actually will think is easy. All right, now, right here, the first skill is that we're going to talk about is just graphing parametric equations. All right, now what I want you to look at before we actually put stuff into the calculator is, do you see right here that what they're doing is they're giving us what they call that t interval, the I, and so here we've got a particular t interval. Here we have a different t interval, but notice that what happens on that one compared to this one. We're taking off the first little part. In other words, this one starts at -2. This one started at -3. This one ended at 1. That one ended at 3. So we're going to have the same functions, but we're going to graph them for different t values. So that means the part of a graph we get is going to be different. All right, and then finally we'll graph this one. Now, would you take your calculator out? Now, I'm going to move mine over so you can see the equations for a minute. All right. Now, I want you to put your calculator in parametric mode. So right there where that's blinking, put yours in the same place and press enter. All right. Now, press y equals, and I've got something in here from calculus. Let me just clear it out for a minute because that looks too interesting for us to do yet. We wouldn't understand it yet. All right. Now, notice that right here, when we look at this, it's got an x sub 1t and then it's got a y sub 1t, so it's got two equations. And so it looks different than function mode looks. Yes, ma'am?
Does it matter if it's in degrees?
All right, it will matter if it's in degree or radian if we put sine or cosine in it. All right, the safest thing to do with this is to have it in radian mode. All right, you almost never draw a graph in degree mode, but it will make no difference unless we have the word sine or cosine. Now, before class is over, we're going to have sine and cosine. Right now, we don't need to change that per se. Okay, now, would you type in that first equation, x equals t squared minus 2. So go to the variable key and touch it, and notice that when you touch it, it gives you a t instead of an x. And it was called the variable key because if we're in function mode and you touch that key, it's going to give you an x. If you're in parametric, it's going to give you a t. When we learn about polar, it'll give you a theta. Okay? All right, so we want t squared, and then right arrow to get back down to normal stuff. All right, minus 2. All right, now down arrow, and then just put in 3t right there. All right, now never just start to graph without looking at window. All right, now if you look at window here, you'll see that this looks different. In normal windows, remember it just begins with x min, x max, y min, y max. Well, here we're going to get t min, t max, and a t-step, and then x min, x max, and so on. All right, now, my calculator's in the funky mode because we were doing something in calculus yesterday where we had some really big x and y numbers, so let's start here with our t min. What we're supposed to put to do the a part here is the smaller number there, that -3, we need to enter as t min. All right, for t max, we need to enter the larger number, the other point of that interval. Now, for the t-step, most of you do not have a t-step of 0.1 showing. You have a t-step of something that begins 0.13 something or 12 something. All right, and we want the t-step in these to be 0.1 unless it has the word sine or cosine in it. So just put a 0.1 there. All right, now, when we don't know what a graph is going to look like, we're going to put in for x min and x max, -10 and 10, just like we would in function mode, all right, and leave the x scale as 1. And for y min and y max, we're going to put -10 and 10. And the y scale should be 1. So you need to have all of that changed all the way down. Okay, now, once you do this, I'm going to hit the graph button. And now that graphed rather quickly, but did you see it started in this position right here. It went in that direction, and it stopped right there. Okay, so if we're going to draw that on our paper, we would have to get this endpoint with the exact coordinates, this one with the exact coordinates, and draw the arrows. Yes.
What was the X scale again for
All right. The X scale was 1. The X and Y scales are generally going to be 1 unless we have to make something really big. Okay. Now, there's a bunch of stuff I want us to see about this, and the only way to do it is to do it somewhat slowly. All right. Now, the first thing that I want you to do is I want you to touch the trace button. All right. Now, when you put the trace button on, notice that you see 3 things here. All right. You see that T is -3. You see X is 7, and Y is -9. Okay. Now, first important thing. On that -3 that we're seeing right here, notice that that was the T-min value. Okay? All right? Now, if we're going to draw this graph, in other words, if you do this as a homework problem, and you've got to show me what the graph looks like, if it has an interval with a beginning point and an end point, then you need to get the coordinates here, the 7, -9 of this one. So we'd go over 7 down to -9 here. So I'm just going to put the point right here without being too hasty about anything else on it. All right. And we'd put that point in that position. All right. And now we would draw the curve the way we think it looks here. So now all I'm going to do is I'm going to put -2. It looks like it goes through that. So I'm going to draw down like this. And then I'm going to come up in this direction. Okay. And now we'll finish that off in a second. But now on the on your calculator, what I want you to do is I want you to hit the right arrow key 1 time. All right. Now, when you do that, all right, notice that the T changed from -3 to -2.9. Do you understand it did that because our T step was 0.1? So it went -3 plus 0.1 to get -2.9. All right. Now, the other thing, though, is though I did a right arrow, did you see that the cursor moved to the left? All right, now that doesn't happen in function mode, but it can happen in this mode. All right, and so what you need to understand is that your left and your right arrow keys control T. They don't control X. Okay, that might be worth writing down. I mean, it might be that you just will realize that, but it's one of those things of the left and right arrow keys are going to control T. Okay, so now we could go on like this. All right, now most of the functions that we had before still work. All right, let me give one more point here, then I'll answer your question. All right, if we were going to do this graph on paper to turn in, we would want to know the endpoints of this other coordinate right here. And so what we could do here is we could go second calc like we've done before. And now notice when you go second calc, it gives you value, and then these other things here stand for calculus stuff about derivatives. So what that means is we can't do min, max, intersect, 0, any of those things that we can do in function mode. All right, but now if we put this in as value, notice this says T equals, and so if we'll put in this -1 right here, I'm sorry, it's a +1, my fault. Thank you. All right, if we'll put in that 1, then it'll give us the ordered pair up at that other endpoint. So that's -1, 3, and we can come over here on our graph and write -1, 3. And this is the kind of thing I would expect you to turn in to me for that. So if you had that problem, then for the A part, you would turn into me this graph. Okay? All right. Question?
Oh, my calculator just wasn't working.
Okay. All right. Let's see. Thomas, are you good with the calculator?
Sure.
Why don't you just move up one and help there? Because that'll be easier than me trying to stop.
Where do we draw the arrows on this graph?
Oh, okay. Where we draw the arrows on this one. All right. We went from here up to there, so we would draw arrows like that.
You would not want us to draw especially choices.
We're not what?
No, you can go to the right.
No. In other words, if I just draw it anywhere on here, it indicates the direction. So if I put the arrow going in this way, we know that that was the starting point. Okay. All right. Now, I'm not going to do the little drawings on the side for the next couple things here. I just want us to learn what the differences are in the different things. So now, I am going to do this. I want to draw right over the top of this drawing for a second so we can see where that was. All right, now go back to window, and I want us to do number 2. Change this to -2, and then change the Tmax to 3. All right, now if I hit the graph button, the reason I wanted to have that drawn up there in red is, do you see that the starting point for the other one is, in other words, we left out some of this, but it started here, and it had these same points on it, but it went on up further, okay? Now, we could do all the things that we did with A to B. We're not going to take time to do that now. The point is, hey, it shows part of the graph in a different place. If I choose the other thing. All right, now, if we go back to window again, and we change this to -3 to 3, all right, then we get all that from the beginning place here up to where that ending place was. All right, now, let me ask you a quick question here. Do you see that what it really looks like here is that this graph is a parabola that opens to the right? That's what it looks like. But instead of having a whole parabola, you know, where it goes infinitely far, we just have an arc or a part of the parabola. Okay, and so that's the thing that's there. Okay, now, if we wanted to get the whole parabola, then our t interval would have to be this. -infinity to infinity. All right, now, I think you can tell, well, how do I put -infinity to infinity in a calculator and get it to graph it? And obviously we can't do that. Anytime that they give us an interval for t that's -infinity to infinity, we will normally put in -10 to 10. And if it goes all the way across our screen, then we're good. If it doesn't go all the way across our screen, we'll adjust those numbers to where the graph goes all the way across our screen so we can see what it looks like. Okay, now, let me put this down, go to the next thing. All right, on this next part, there's sort of fundamental ideas that you need to know. And so I would refer to this as being a skill of how do you find points on a given parametric curve. All right, now, if you can do this by hand. There's a way to get the calculator to do it as well, and I'm going to show you both of them. All right, so obviously, if we're doing it by hand, when t is -1, then we're going to put -1 into that equation, and so we're going to get 3 minus 1, which is 2, and then we're going to put -1 into this equation, and so 2 times -1 plus 5 is 3, and then we can go on and put the other numbers in there. All right, somebody tell me what the next ordered pair here would be when this is 0. That one's easy to calculate. All right, -1, 5. All right, and then somebody tell me 3, and then after we do 3, I'm going to show you how to get this on the calculator because it's so much faster. All right, if you put a 3 in, what do you get for this one? The x coordinate.
26.
All right, 26, and what was the y? All right, 11. All right, now take your calculator out and go to y equals, clear what's there, and let's put in this one. So we want 3t squared minus 1. All right, and then we want to clear this one and put in 2t plus 5. All right, now on the next thing I want you to do, I want you to go second format. All right, anytime that we have to fill in numbers in a chart, we want to be observant about one thing. Do these numbers go up in a pattern? Yes or no? All right, they don't. All right, if they don't go up in a pattern, then we need to go over here and change the independent thing to ask right there. All right, so do that. let's see, let's go down to here. Go over to ask and press enter. All right, now go second table. And when you do, you'll see that it's got a little chart like we have here. And now all we need to do is just type in our t-values. So if we put in -1, then it fills in the stuff. We put in 0, we put in 3, we put in 5, we put in 5 divided by 2, and it gives us the numbers. Now, I think you can see that's nice and quick, right? Okay, now, questions?
The table setup.
All right, you go second format, and you change the independent variable to ask. Okay, now, everybody good with just getting that part? So anytime that they tell you in homework tonight that they just want you to write a set of ordered pairs and fill in a chart, then you want to use your calculator to do it, and it's nice and simple. Okay? By the way, I know some of you do this along as I do it. If you don't, instead of just watching me do it, you don't remember it later if you watch somebody do it. But there's something about when you connect your fingers actually going and doing the thing on your own, you will tend to remember more later. So try to work along there, if you will. Okay, now I want to take this same idea, and I want to. We're going to keep this same set of equations for a minute. Suppose that they had told us, suppose that they told us that they wanted us to get the ordered pairs, but they did it like this. Let's say the first one was -2, then -1, then 0, then 1, then 2, like that. All right. If there's a pattern to that where it just goes up 1, then instead of us doing what we did last time, we could come over here to put this, let's see, go back down to where the ask was and change that back to auto. All right. And now if we'll go back up to the start, we can tell the table to start at the first number in our table. So -2 in this case. And then the delta table means the change in table. How much do you go up each time? So we would just go up 1. All right. And so now if I do that, and then I go second table, then it's going to fill in the table with those values. And it'll just fill it up for as far as it can go. Now, if we only want down through 2, we just ignore the other numbers. All right. Now, does that make sense to you? That should happen. All right. Now, let me just try one more thing for you right here. Suppose we wanted to go -2, 0, 0, 2, 4, 6, etc. All right. Go back to second table set again. What would we change to get it to be this? All right. Delta table change to, all right, to the number 2. All right, and if let's see, I hit graph instead of second table or second graph. All right, but if we do that, then it gives us those numbers like that. All right, questions or comments? All right, so that's supposed to be a fairly easy skill. Okay, next thing. All right, you will not have a just automatic knowledge of what a graph is going to look like when it's in parametric form. All right. As a matter of fact, you can get infinitely many parametric equations for most common graphs. Like if you were going to graph y = x squared and you wanted to do it in parametric, you can do it infinitely many ways. All right. Now, the fact that you can do that is one of the reasons that people don't talk about parametric as the first thing. They talk about functions instead. Okay, because functions are more direct. But now, if somebody gives us something that's in parametric like this, we may or may not know what it looks like just by looking at it. Like, if we backed up here to this, how many of you could look at that and say, I think it's a parabola opening to the right? And the only reason I can say that is, remember when I accidentally mishit it and it showed the parabola opening to the right? Okay, it was a parabola opening to the right. but it's not something I would know just by seeing the equations. Okay, now on one like this one, you might be able to guess what this one's going to be. All right, because it's going to turn out to be a common graph. Okay, but if we want to check to see that something's right, when we do work by hand, one of the things that we can do is we could convert the equation from parametric form back to function form, and then we would understand what the function equation was usually. So in other words, if we got something in the form y equals mx plus b, then you would say it's a line, right? Or if we got something in the form y equals ax squared plus bx plus c, you would tell me it's a parabola, right? And so there's certain things that we just automatically know if they're in function form. Okay, so now, if we're going to take one of these functions here that's in parametric form and convert it to function form, that is called normally eliminating the parameters. The parameter's the little letter t. So if you eliminate the t here, you'd get x's and y's. All right, now, there are two rules for eliminating the parameter. All right, one of them is, the first one is, in one of the equations, solve for t. Okay, now, it would be easy enough to solve for t in either equation here. All right, but let's solve for t just in the one on the left. So we would get here t equals x minus 1. Okay, now, the second rule says substitute the expression for t, so that would be this x minus 1, into the other equation, and then solve for either x or y. Now notice this one's already solved for y. Okay, now, what's this the graph of? All right, a straight line. Now, more than just being a straight line, you know stuff about this one. Where does this one cross the y-axis? All right, -2. What's its slope? Okay, now put this in your calculator. All right, now because it's given us the t interval as being -infinity to infinity, put in -10 to 10. Okay, and then see if it graphs with a slope of 2 and a y-intercept of -2. All right, do that.
Mr. Agent,
Yes, ma'am.
how do you do the window?
All right, for just the regular graph.
For this?
Okay, for the one we're doing right now. All right, just go second. Not second window. Just go window. All right. Now, when it's got -infinity to infinity here, we said that'll be -10 to 10. All right, and then our t-step is always going to be 0.1 unless we have sine or cosine in it. Okay, and then it's good to just let the others be -10 to 10 unless we need to change them. Okay. Okay, now if you look at that graph, I think you can see it's going through -2, and it's got a slope of 2. If that view makes it where you can't tell that the slope is 2, you can go zoom 4, all right, and you can see it easier. That's up 2 over 1, so it has a slope of 2. Okay, zoom 4 just gets it closer to the origin, and you can see better. All right, now. Tell you what, before we go to this one, let me go right here for a minute. All right, would you eliminate the parameter there and get this as a function either of x or y? I thought I had another slide in there where we would do that, but I must have taken it out by accident. Okay. All right, I'm just going to be background noise while you're doing work for a second. All right, this problem's a lot harder than the one we just did, but it's not an impossible problem, but you get sort of an ugly looking answer. And so when you start getting into it, you're going to have questions like, how far do I need to simplify it, etc. So, do your thing. Well, if you want to try to, the reason for doing this is so we can tell what that other shape ought to be. In other words, if you did not have a calculator and you were just looking at those other equations, you would not, in that last case, have known it's a line that has a slope of 2 and a y-intercept of -2. You would not know that. And therefore, if you change it, you would realize, oh, it should be a line.
So you'll get the same graph if you did the original.
Yeah, all right. If I graph this in parametric mode and I graph what you get as an answer in function mode, they should graph into the same thing. Yeah. That's what we're going to show you. All right. Which equation did you use to solve for t? All right, the first one. All right. When you got through solving there, what did you have? T was equal to what? X over 3 minus 7. Okay, so now I just want to put work for this in just a little bit. So I'm taking it. Did I write it the way you got it?
Wait, why wouldn't both be over 3?
Yeah, I was thinking. Yeah, that's why I was going back to check. All right. Now, so let me put the steps in because I didn't agree with the answer. All right, it should be x minus 7 equals 3t, right? And then when you divide by 3, you'd either write it like this, or you could write it as t equals x over 3 minus 7 over 3. All right? Now, when it comes to which of these should you write, if you're going to plug something in, would you rather plug this in or would you rather plug that in? The first or the second? It might be to you where it doesn't matter, but right here, do you see this has got 2 fractions in it? That just has 1 fraction. So if I'm doing it, I'm going to make it where it'll have 1 fraction. So I would write it like this. Okay, now, remember the second rule was, since this is what t is equal to, because that's t right there, then we're supposed to come down and where the t is in this other equation, we're supposed to put what we had. Okay? And so we would get this answer right here. All right, now, can you tell what that graphs into? All right, it graphs into a parabola. Okay, now, so we could be convinced that it should graph into a parabola because it's going to have an x squared. All right, how many of you would generally not leave an answer in this form? Notice you get rid of the parentheses, right? Because if you get rid of the parentheses, you can tell more about the parabola, okay? And so we could do this. So if we do x minus 7 squared, all right, that part, then that's going to be x squared minus 14x plus 49, all right? And then if we square the 3, we're going to get a 9, and then we're going to get a minus 6 here. Let's see. All right, so we could write this as x squared over 9 minus 14/9 x, and then this is 49 over 9, and if we go minus, this would be 54 over 9, and so this would be the same as minus 5/9. Okay, now, that didn't turn out to be very pretty, in any sense, all right? But in the homework, they're going to give you problems where you're going to do the technique that we just did here, okay? All right. Any comment about that?
So we have to do something.
All right, well, I'll put it this way. On the test that I used to give, because I promised you I would give you a different list here, I put problems like this that were multiple choice. And so, if you did something and you got this answer, you'd have to look down across the answers to see if they had it with the parentheses or not. And sometimes they didn't, and you have to simplify it out. Does that answer your question? Okay, so as a math teacher, I would tell you, I would leave the equation solve for y in the way that I would recognize what the graph should be most easily. Okay, so if you have to get it down to this to realize it's a parabola, in other words, parabolas can either be in this form, ax squared plus bx plus c, or they can be in the form y equals a, and remember how we went x minus h quantity squared plus k? Those are the two forms we know for a parabola. All right. If you can tell from right here that this is going to be in one of the, I'm talking about right there for the people who having to see this later. All right. If you can tell right there that this is going to simplify to that, then it's all right in my mind if you stop. But if you're not sure that that's going to happen from there, then I'd say simplify it down to this, because this part right here is definitely that form. Okay. All right. Now, if we have one of these problems and it has the word sine or cosine in it, all right, then to eliminate the parameter, you have to make use of a trig fact. Okay, so I want us to look at this one for a minute. And the work is here already. But here's the first equation. There's the second equation. And now I want you to look at that parametric interval right there. It goes from 0 to 2 pi. Remember, if you go from 0 to 2 pi, you go all the way around the unit circle. Okay, so you get all of the cosine values, all of the sine values, because it's periodic and it just starts over. All right, so a lot of times we're going to have a parametric interval that's 0 to 2 pi. Now, take your calculator back out for a second. I'm demonstrate. There's a reason I'm telling you this. All right. When we have graph before in function mode, do you remember that there are times when we have gone zoom 6, that's zoom standard, and it moves everything back? All right. Now, I'm in parametric mode right there. If I go zoom 6, I want you to watch what happens. All right, now, I'm not so interested in the graph. Now, notice though, we didn't get the whole line. All right, but now go to window. All right, because when you do zoom 6, it changes some things. All right, now, I should have checked something before I did this. All right, we've been doing some stuff where in order to get an angle, we needed to get the angle in degree mode. All right, and so my mode right here is degree mode. All right, when you graph something that has sine or cosine, you want to get out of degree mode into radian, and I had not done that. All right, so let me go back to where I was for a minute. If I go second quit there, and now go window one more time. All right, if you see a 360 down there for T max, it's meaning 360 degrees, and that will alert you that you're in degree mode. Now, I want you to look at the T step. It's 7.5. All right, now 7.5 happens to be 360 divided by 48. Okay, so it's like getting 48 points around in a circle. So it's enough points to draw a graph well. All right, now let me change my mode. All right, back to radian. So I'll get what you got. Now if I go zoom 6, all right, and then go back to window, notice that it goes 0. Do you recognize that number right there is 2 pi? So the reason I'm telling you this is this. This happens so often in parametric that it's considered to be what is standard when you do it. Okay? In other words, in parametric, a lot of the times, in the useful purposes of it, you get a bunch of stuff with sines and cosines, and so you do this. Now, this number right here, that 0.1308, somewhere on your paper you need to jot down that that's pi divided by 24. Okay? Because there's going to be a time you'll have to enter that in to get that back. In other words, you'll have a t-step of 0.1, and instead of going and doing Zoom 6, if you just want to change that t-step, you want to just remember it's pi divided by 24. Now, you'll see on the rest of this was negative 10, 10, negative 10, 10. All right, now, while we're at this window, let's see, let me put that down. I need, the reason I just did all of that stuff that we did here is to show you that your calculator honors that 0 to 2 pi thing with parametric. So if you do Zoom 6, it gives you this. All right, now, if I have this as my function, don't copy what I'm going to write. I'm going to show you the way to screw this up, that if you follow the directions that I gave you back here, it will screw up if you got a sine and cosine in it. Okay? This works fine as long as it doesn't have trig function. All right? And the fact is, it'll work for the trig function, but you got to know some stuff that we don't know off the top of our head, and therefore it's better to avoid. Okay? So, right here. If I tried to solve that first equation there for t, I could do this. I could get x over 3 equals the cosine of t, and then to get t by itself, I'd have to do cosine inverse. So I'd get cosine inverse of x over 3 equals t. All right, so I've taken one of the equations and solved for t. Now, if I plug that in to the other equation in place of the t, we would get 3 cosine, I'm sorry. I got to focus on what I'm writing here. All right, we would get 3 sine and then cosine inverse of x over 3. All right, now, do any of you recognize that equation? I'm going to guess not, right? I mean, if you showed that to me just out of the blue, I wouldn't have any idea that that was a circle with a radius of 3. All right? Because that's not normally how we get a circle, right? Okay, so right here, if you have sine or cosine, I told you not to copy this because you'll come down here and you'll get stuff that's got trig functions and inverse trig functions, and we don't know enough about the graphs of those to understand. Okay, so when we see something with the cosine squared and the sine squared, we're going to do the following. All right. In essence, we're going to make use of the fact that the cosine squared of t plus the sine squared of t happens to be equal to 1. Now, how many of you remember that trigonometry from Algebra 2? All right, because it's a big deal. Okay? All right, so right here, if we're going to do this one, every time that we see same two things here, same two numbers here, then what we're going to do is we're going to square the x. So x squared will be 9 cosine squared of t. All right, and then y squared will be 9 sine squared of t. And so we want to write it like this. We're going to go x squared plus y squared because we recognize that if I've got cosine squared and sine squared, so here, this is 9. It's going to be what they wrote here. I did the introduction, and then you get x squared plus y squared equals 9 cosine squared plus 9 sine squared. Now, we're going to factor out the 9, and right here, we're going to have the cosine squared plus sine squared of t, and since that's equal to 1, we can put 1 in its place right there, and so now our equation becomes what we have here, x squared plus y squared equals 9. Okay? Now, about the only time that you have to concentrate on this one is when these two numbers turn out to be the same right there, then you'll do the problem this way. Okay? In the homework tonight, there's several problems that are of the type that we had right here. Okay? And then there's 1 or 2 that are of this type. And so every time you just see a sine or a cosine, you got to remember this. So this is one of those things of like, it's like a special case, but you got to know something about it. All right. Now, on this next thing, we're going to talk about writing parametric equations for a line. And I'm going to tell you, there is a way that the book does this, all right, and it involves vectors. And there's an example in the book, and if you happen to have a tutor and you go to your tutor's going to try to teach you that way. And I'm going to tell you, it's fine if you do, but I'm going to show you a way that's different, that's easy to understand, and we're going to go with this other way, all right? I want you to write x equals y equals like this. And I want you to write here x sub 1, y sub 1. All right, now, the x sub 1, y sub 1 should represent the ordered pair that is farthest left on the graph. Okay, so x1, y1 is ordered pair just between the two of these, that is farthest left. Now, if you happen to put in the one that's farthest right, it just changes one little fact that I'll show you at the end. Okay, now, right here, I want you to put delta x times t. And here, I want you to write delta y times t. Do you remember when you do slope that you do y sub 2 minus y sub 1 over x sub 2 minus x sub 1? All right. In science classes, this is called the change in y, so it's usually written delta y. And this is called the change in x, so it's usually written delta x. Okay, so the way we're going to get the equation for a line is this. We're going to do the slope with these two ordered pairs, and we're going to put the one that's farthest to the right in as the first thing on top. Okay, so right here, this point right here has an x coordinate of 2. This is -3. That one's farther right. Okay, so if I do the slope, I'm going to go 3 minus 6, and then I'm going to go 2 minus a minus 3. All right, so I'm going to get -3 over 6. Over 5. All right, now I'm running into where I had that other stuff, so right here, I want to write -3 over 5, and I want to write delta x over delta y. Okay, now, in case this would turn out to be something like 4 over 6, 5 over 10, that'll reduce. I'm going to tell you, don't reduce unless you are going to change the parameter interval at the end. So it's best to leave it just with whatever numbers you get. Okay, now, right here, we've identified a delta x, we've identified a delta y, and then I've told you how to identify an x and a y here. So all we need to do is fill in that pattern. So we're going to go x equals -3, all right? Hold on a second. I won't, let's see, wait. I wrote something wrong right here. All right, y'all let me sneak away with it. Right here, y is going on top, right? Should be delta y over delta x. All right, my fault. All right, so right here, we're going to write -3 plus, and now the delta x is 5, and I'm going to put a t. In other words, I'm just filling in that form. Okay, and then down here for y, I'm going to go 6. That was my other ordered pair, right? All right, 6. And then since this is negative, I'm going to go -3t. Okay, now, if we want to graph a line, then our parametric interval has to go -infinity is less than t is less than infinity. All right, so this is the equation for the line that goes through those two ordered pairs. Yes, ma'am.
I'm more confused on, isn't X one, two?
All right, read this part right here. X1, Y1 is the ordered pair that is farthest left. Okay, so if you graph these two ordered pairs in a plane, -3 is to the left of 2, so this one would be farthest left. That's why I wanted to use this one.
For the slope?
No, for the X1, Y1 right here. No, you were asking me why was that -3, right?
But don't you use the slope to?
All right, you put the slope right here in these two places.
Okay.
Okay, all right, and up here, delta X is the one on the bottom, and delta Y is the one on the top. So that's why they go like that.
So is X the farthest and not Y?
Wait, now I'm missing what you're saying. Yes, yeah, when it's, all right, if I'm graphing in a plane here, all right, if I graph 2, 3, all right, I'm going to go over to 2, and then I'm either going to go up or down. All right, so it's 2, 3, so it's there. All right, when I graph this one, this is -3, and then it's -3, 6. Okay, so that's on up here. But do you see this point with the x coordinate that's negative is to the left of the one that's where the x coordinate's positive? That's all that was saying. Okay. I didn't mean to make that complicated, but it's easier if you do it this way. Now, this is the equation for line. Now, I want you to take your calculator out, and I want us to see that this is true. Okay, so I need to move this over for this one. All right, so I want for x sub 1, -3 plus 5t. And then for y, I want 6 minus 3t. All right, go to window, and I want my window to go from -10 to 10. And I want my theta step, t-step, to be 0.1 because I don't have a sine or a cosine. All right, now I'm going to graph that. Okay, now consider something with me right here. If I put in a 0 for t in both places, do you see I get -3, 6? So right here, I'm going to go second calc value, and I'm going to put in the t number 0. All right, and it should show me the -3, 6. So I know that the ordered pair that's B is on my graph now. Okay, now I'm going to put in a 1 here. All right, because if you do it this way, when you put in a 1, I should get the other ordered pair. And so now, do you see it doesn't matter about the other junk? The two ordered pairs are on the line, and through any, it's got to be the right line, because through any 2 points, there's exactly one line. And so this has to be a correct set of equations. All right, now, several things. All right, number one, are there other equations that you could write for a line that would go through those same 2 points? The answer to that's yes. All right, now, most of them are things like this. They're related to this where you could negate both of these and negate both of those, and you still get the same thing, I believe. All right, but it's something that's related to it. All right, and so this turns out to be the easiest way that I've found to get students just to be able to get that right. In other words, look at this and you'll understand where what I just did came from. All right, this -3, 6 was about right here. And then if I'm going to get to that point there, do you see that I'm going to go over this amount? So that's my delta x. And I'm going to come down this amount. That's delta y. And so if I start here, all right, so what I'm saying here is start at this x number. And then if I add this delta x to it, it ought to bring me to that number right there, which is that next point. And then if I start with this y and I move, in this case it'll be down because the delta's negative, the delta y is negative, all right? If I move down this much, all right, and come over to there, then the y coordinate here is going to be the same as whatever this original y plus delta y was. And so that's where that's coming in to get that. And if you want to read the example in the text with the vectors, I'll say, go ahead and do that. But I've tried to teach it that way at times before and found people get really confused with it. Here, the one thing I don't like about this, and you understand that we don't do as much, I rarely ask you to memorize that something that's not in the book. Okay? This is something that's not in the book, but it's the easiest way to do that. Okay, now, real quick, because the bell's going, I did the wrong thing. I want this one to go down. All right. Now, let's see. Let's go back to here. The next thing I want us to do is talk about writing parametric equations for a segment. All right. Now, to do a segment, you do it exactly like this. All right. And the only difference is, so right here. All right. To get the equation for a segment with given endpoints follow the procedure for a line and make the interval 0 to 1. Okay? All right. Now, I'm going to back up to just try to explain that, because in problem, I think it's 27, it's 26 and 27, you're graphing a line, and in 28 and 29, you're graphing a segment. And so you do them all alike, with the exception of when it's a line, you go negative infinity to infinity, and if it's going to be a segment, you're going to go 0 is less than t is less than or equal to 1. All right. Now, I will expect you to have most of the assignment at the end of that done. If it covers stuff we haven't done, then you don't have to do that part. Yes, ma'am.
If you press the stop button,
Huh?
or turn the stop button.
Yes.
And you can press the stop button at the top.
Oh, it's right here, yes.